Good morning, everyone. Happy Monday. So we are talking about, we're in the fourth unit of this class, which is analyzing systems for their stability. So let me switch over to the slides and we can get a quick recap. Okay, so we are going to be talking about whether the poles of a system are in the left or the right half plane. That's basically what we're reducing the notion of stability to. So we have these definitions about the at least two different kinds of stability. But what we're going to mostly treat, actually what we're going to exclusively treat, is if we know the poles are in the left half plane, then we're stable. If any of the poles are on the imaginary axis or in the right half plane, then we are unstable, or we're going to treat that as being a bad condition. We also have to be careful that which poles are we talking about, right? So are we talking about the poles of a subsystem, or are we talking about the poles of the overall input to output, what I'm going to call the closed loop system? And those are mostly what we're going to be focusing on. So this slide that we have on screen was our quick little demo to show that stability or instability of any of the blocks really doesn't tell you a whole lot about stability or instability of the system as a whole, viewed as a input-output relationship. So the tool that we are going to use to analyze system stability is called the Routh-Hurwitz criterion. And the idea behind this is way, way back in the day. This result actually dates from like the 1880s, that kind of deal, where machines were getting more complicated. So you think like steam engines, that kind of deal. And yet people wanted to control them with more accuracy, if you like. And the first step in controlling a steam engine would be making sure it doesn't blow up. Okay, so there's some motivation, some historical motivation for this. So if you have a mathematical description of your engine, you would like to design a controller that makes sure it doesn't blow up. So the idea here is that the power output from the engine would then somehow control the valve that let the steam into the engine. So you get a self-regulating system. So that's the context in which this stuff was developed. And it actually kind of goes towards, like, it has this very arcane feeling, right? It's this table of values, and you're supposed to do all these determinants, and all. It feels old-fashioned, and that's because it is old-fashioned. But that's not to say it's not useful, and I hope to convince you of some of the use cases today. So that was a huge historical tangent. Let's get back to talk about what the Routh-Hurwitz criterion is. And again, it's a promise that if you can count the number of sign changes in the leftmost column of this array, then you will be able to know how many roots of the polynomial are in the right half plane. Okay, that's the promise. We're not going to tell you where exactly they are, but you are able to determine, are they to the left or are to the right? And if you are designing for stability, that's really all you care about. So that's what makes this a useful tool, even in this day and age. Now, you can say the criterion very simply. It's much more difficult to describe how to formulate the array on which the criterion is applied. So we're going to do some more examples today to reinforce that. So here's where we're going to pick off. I think it's page 11 of your handout set. So the task is determine the range of the variable k that produces a stable closed loop system. Okay, that's a very simple statement. If we want to test stability of the closed loop system, which polynomial do we need to analyze for the root locations? Is it this one, or this one, or none of the above?
None of the above, since we need the closed loop system.
Right, we need the closed loop poles. So for that, we need the closed loop characteristic polynomial, which is found in the denominator of the closed loop transfer function. Good. So we need the closed loop transfer function first. So again, yeah, I think you're probably starting to see why that like feedback reduction rule that we learned first week was pretty important. It's basically the start for everything. So what are we doing here? We're going to do the forward path over 1 plus forward times feedback, that same rule, s squared plus s plus 1 times s plus 2 over 1 plus that same thing. So this is not in a form that we can extract the characteristic polynomial from. So let's multiply through top and bottom by this denominator in the denominator. So this ends up being k on top, s squared plus s plus 1, and then s plus 2, and then plus k over here. So that's actually the kicker. And this is, I hope you can see that the closed loop characteristic polynomial, which again is this denominator. So we're gonna need it. So let's just write it out. Closed loop characteristic polynomial. If you FOIL all this out, you get s to the 4 plus 3s to the 3 plus 3s squared plus 2s plus k. So my point is that this is a regular old polynomial, except this is a variable. And if you try to plug this into your root finding algorithm, you're not going to get very far, because the very first step in entering your root finding algorithm is to tell your algorithm what the polynomial is. And we don't actually know what it is yet. That's the point of the question. Okay, so I think when I teach this, people think, well, I spent $500 on my calculator that can do all this stuff. And my point is that no, you have a very nice calculator. That's good for you. But I don't think it can do this, not unless you iterate, not unless you write a for loop that explicitly tells it to do this. So we can, however, formulate the Routh array even if we have variables in our coefficients. So let's do that now. So we're going to make the Routh array out of this. This is what, fourth order? So we go s to the 4, 3, 2, 1, blast off. All right, I'm going to assume that you're smiling. Okay, so let's remember how to fill in the array. We go serpentine style. So 1, and then 3, and then 3, and then 2, and then k. And who remembers, what do I put here? Like what goes underneath the k?
Is it a 0?
Yeah, so we ran out of coefficients, which means we are free to draw as many zeros here as we like, including this one. And this is the most important one. Okay. All right, so I'm going to go kind of slow today because I don't think we have a full hour's worth of content. Those are famous last words, but I think you might enjoy going slow here. So this coefficient, we'll call it b sub 3. That is, what, 3 times 3 minus 2. So that's 7 over 3. 7/3. Okay, so once again, that was the kind of the backwards determinant. That is this diagonal minus that diagonal, and then always normalized by this coefficient here. And let's do b sub 1, which is 3 times k minus 1 times 0 divide by 3. And this pattern is worth noting. So we've got 1, 3, k, 0, determinant of that, negative of that, divide by 3. Do you see here that whenever there's a 0 in this position, that this product will always be 0? So we don't have to worry about that. But what does that mean? That means the only product we're looking at is this product. And then we're straight away going to divide by that coefficient there. And so what I'm trying to get you to see is that if you have a pattern that looks like x, y, z, 0, divide by z, this will always be y. I mean, work it out for yourself. The determinant here is x times 0 minus z times y. So the x times 0 doesn't matter. So inside of the bars, we just get z times y. Oh, sorry, negative z times y. This negative cancels that negative, and then we divide by z. So we always have to end up with y, regardless of what we're in the other positions. And the key to that is this 0. And so I'm going to use that to actually shortcut a lot of these entries. Because here I have 1, 3, k, 0, k automatically. We can keep going if you like, but the idea is that we're going to end up taking determinants with all 0 columns. And so that is going to be 0, as well as that, et cetera, et cetera. Dot, dot, dot. Did I lose anyone? Anyone have any questions on that?
So isn't when you did the little calculation on top, isn't that y negative? So wouldn't you have like a sign change?
So let's be clear here. Okay, so let's just do what's inside the bars. So we'll get the negative out here and we'll get the z down there.
Mm-hmm.
So inside the bars, we get x times 0 minus z times y.
Oh, okay.
Yeah, it's, again, it's hard for me to see as well, but this and that will cancel.
Gotcha. Thank you.
How did you get 7/3 again for s squared?
Sure, so I guess I should stop taking shortcuts if I tell you we're gonna go slow. So this is b sub 3. And that means it's the negative determinant of 1, 3, 3, 2 normalized by 3. So this is 9 minus 2 over 3.
Okay, got it. Thank you.
Yeah, you're welcome. Okay, are we ready for the C row? Because here's where it gets complicated. Okay, so C, we'll call that C3. And again, it's the determinant of the 4 entries directly above it. So that is, what, 7/3 times 2 minus 3 times k divided by 7/3. Okay, so this is what I'm calling the reverse determinant, which is bottom left times upper right minus upper left times bottom right, and then always normalized by the leftmost entry in the row above. So another pattern that you're going to end up seeing is that this first term is always going to be divided by that same entry. So this will always be just the upper right entry of the determinant minus, what is it, 3k over 7/3. I think that ends up being 9/7 k. So C3 is calculated. C sub 1, check this out. We've got a column of zeros. So we can automatically say that's 0. And this is why this algorithm terminates, is because you end up getting these zeros that creep in from the right. And so you will never get a row that's longer than the row above it, which means your rows will tend to get shorter, which means the algorithm will tend to terminate. Okay, lastly, we got to calculate D sub 3.
Oh,
but, yeah, who's that?
Oh, this is Jeremiah. Hi.
Okay, go ahead.
What was that? What's that day next to the check mark? Is that L3 or L sub 3?
So we label these as new letters every row.
Gotcha.
So these are the 2 A rows, and then the B row, and then the C row.
Okay.
So that was my Monday morning, only half a cup of coffee, C.
Oh, no problem. Thank you.
Yeah. Oh, right. I was saying that we get to use our new trick here for D sub 3. So who can tell me straight away what D sub 3 is going to be?
K?
That's right. So we get to use our fancy teleportation trick. So you see this is X, Y, Z, 0. And so the K comes straight down. And this is super handy, right? Because C3 is really ugly. And so if you did your determinant, there's lots of chances for, arithmetic errors. And so use this shortcut anytime you can. Okay, so once we have the leftmost column of the Routh array formulated, we are now able to apply the Routh-Hurwitz criterion. So that says check for sign changes. So let's go change colors. This is a positive number. This is a positive, yeah, sorry, this is college, I know, but these are positive numbers. So far, if I go down, there is no sign change. If I go down, there is no sign change. If I go down, there is an unknown sign change because we don't actually know the sign of C3. The sign of C3 is determined by K. So let's go and work that out. If I want a stable closed loop system, tell me this, do I want C3 positive or negative?
Positive.
Positive.
We need a leftward eating alligator here. We want C3 to be positive. That would mean that there would be, so far, no sign changes. So if C3 wants to be positive, then we have an expression for C3. This is 2 minus 9k on 7. What do you want to do here? You want to move the 9k on 7 over so you get 2 bigger than this. Multiply through by 7/9, which is positive, so the alligator doesn't change. And we get k has to be less than 14 over 9. Okay, so if that's true, then we can replace this question mark with no sign change. And then if we treat C3 as a positive number, then what we need is for k to be positive as well. So once k is positive, we have our range, and then there's 0 sign changes. So there are, if we enforce the bounds that we just found, there are no sign changes in the left-hand column, which means that there are no roots of the closed loop characteristic polynomial in the right half plane, which means that the closed loop system is stable. So this, well, that's the logic train that explains why this is our final answer. So I'm going to harp on this one more time, but this is something that's actually really tricky for a calculator or a computer to do. Right? Again, it's not impossible. You could iterate, you could search through the space of all k's, and you could find ones that produce stable versus unstable systems. But I'm pretty sure that once you get the hang of this, you can do this faster than you can search all real numbers for valid gains, like even with a fast computer. Okay. But the idea is that if you have variables in your polynomial, you work out the entries in the Routh array in terms of those variables, and then at the end, you decide what do those variables have to be to produce no sign changes. Okay, that's the moral of the story here. One more thing I can point out is that this block is called an integral controller. So it is what it does. It integrates the error and it sends that signal to the process or the actuator. And as you might imagine, this integral controller is marginally stable on its own for all k, yeah? But if we allow k to be in this fairly tight range between about 1.5 and 0, then the closed loop system, so the system, if you black box this, that system is stable, regardless of the marginal stability of your controller. Let's try one more example, this time with 2 variables. So same prompt, what kind of gains Kp and Ki make this system closed loop stable? Do you want to take a crack at this? Let's see, check the time.
Sure.
Yeah, take 5-ish minutes. See how far you get. I'll catch up with you in a bit. Feel free to ask questions in the chat or over audio. I'm just going to hang out.
Could I verify the closed loop transfer function before I do too much more? Is that
Go for it. Lay it on me.
okay? So on the numerator, I have s times k sub p plus k sub I.
Mhm.
And then in the denominator, I have s times the sum of s plus 1 times the sum s plus 2 plus s times kp plus k sub I.
Yeah, that's right.
Thanks.
Okay, if you don't mind, I think I'm going to take over and catch up, but please feel free to keep working until I catch up with where you're at. So yeah, as the disembodied voice confirmed, we have a closed loop transfer function that looks like S times Kp plus Ki divided by the product of all the denominators plus skp plus ki. And so if you were wondering, if you had trouble getting to this point, I think a nice trick would be the controller was here presented to you as the sum of a proportional term and an integral term. But I think because we're going to be working with polynomials, the very first thing you want to do is actually to make this a single fraction. So that's what I've done here in red, and that allows me to, I think, take it a little bit easier through the rest of the problem if you combine these into be over a single fraction over S. So we're not after the closed loop transfer function, we're actually only after the closed loop characteristic polynomial, which you get when you FOIL out everything down here. And according to my notes, this looks like S to the 3 plus 3s squared plus 2 plus kp times S plus ki. Okay, so again, this is a polynomial whose root locations, either left or right half plane, dictate the stability, either stable or unstable, of the closed loop system from R to Y. So let's plop it into a Routh array. So this is third order, which means we start S to the 3, and then 2, and then 1, and then S to the 0. And 1, 3, 2 plus kp, and ki. Right, so yeah, third order means 4 coefficients. And here, this looks like 3 times 2 plus kp minus ki divided by 3. And here, if you like, is going to be a 0 because of these imaginary zeros that we put out there. Sorry, not imaginary, make-believe zeros. Right? Imaginary means something special for us. Again, I'm assuming that you got that joke. A joke in a very loose sense of the word. So then all of a sudden we have this magical 0 in the bottom right, which means I get to teleport the ki down to that corner. Okay, questions on how to get to here?
Just can you reiterate how you got the 2 plus kp for the S to the third order?
S to the 1, but sure.
Oh, I mean for S to the S cubed, I mean up to the very top, you have a 1 coefficient, and then you have a to the right of it 2 plus kp.
Yep. So I filled in the polynomial this way.
Okay.
This is your S to the 3, this is your S to the 2, this is your S to the 1, and this is your S to the 0.
Gotcha. Thank you.
So if we want a stable system, then we have to check for the sign changes in the left-hand column. Because this is positive and this is positive, that then tells me that I need this quantity to be positive. So we need 2 plus kp minus ki on 3 to be positive. And what else do we need? We need ki to be positive. If those two inequalities are true, then we will have 0 sign changes in the left-hand column, which means that there are 0 roots of this polynomial in the right half plane, which means that the system is stable. Okay, so there's several stops in this logic train, and I want to make sure that everyone stays on the train. What else could we say? We could rearrange this, and you'd get something like kp has to be bigger than ki on 3 minus 2. Okay, and that's pretty much as far as we can go. We definitely need ki to be positive, and the bound on kp depends on ki. That's one way to view this. Another kind of handy way to visualize this is plotting this result in the kp-ki plane. right? So in this plane are all possible controller gain combinations, provided those gains are real numbers. And how would we visualize this? We need ki to be positive, which means we're looking to the right of this vertical axis. And if we need kp to be bigger than a line, then I would pick that line, I don't know, something like, that's supposed to be a line for those of you who are mocking my drawing skills. And so this would be the intercept when ki is 0, this would be the point -2 on the kp axis. And this has a slope of rise of 1 and a run of 3. So you tell me, where in the plane is the acceptable design region? Above this line or below it?
Above?
Yeah, because we
Well-
want kp's bigger. So I'm going to shade the acceptable design region. Yeah, so this is our happy place.
I had a good question about the Ks. So
Sure.
the more Ks we have in our closed loop characteristic polynomial, does that mean that it like decreases the amount of area we have where K can exist, I guess?
Well, not exactly, because what would happen if we had a third gain, like a third degree of freedom is the technical term? Then you would actually change this plane into a space.
Oh, okay.
So the idea of like reducing area when you have a three-dimensional space doesn't make a whole lot of sense.
Mhm.
Usually, the more degrees of freedom you have, the more combinations you can have that creates an acceptable controller design.
Gotcha.
I mean, it makes the algebra harder because you get more
Mhm.
things depending on each other. But in general, more degrees of freedom make the controller more designable, which makes your life easier.
Gotcha. Yeah. My thinking was that since we increased the Ks, we would have like sort of, because in the earlier problem we only had like a small range, so I thought we had only like a small range of numbers we could plug in into our system. Okay. Yeah. Thank you.
Oh yeah, sure. I think that if you had a higher order polynomial, like if this was higher order,
Mhm.
or if the controller was itself higher order, but with the same number of degrees of freedom,
Mhm.
then you'd have the k's appearing in more of these left-hand columns, which would mean you'd have more inequalities, but in the same space. And that
Thank
would
you.
end up trimming down your design region.
Mhm. Okay. Thank you.
Yeah, of course.
And quick last thing, the only reason that we sketch this plane and define this, how it's higher, if it's higher than this line, the values were stable, is because there were no sign changes between the first element of this array.
So yeah, let's go back to the beginning, and the 1 and the 3 we can't do anything about, right? They come from the polynomial, and our k's can't touch them. But that's actually a good thing because it establishes the fact that we need positive numbers in this column.
Oh, I got it.
Yeah. So this positive and that positive were kind of handed to us, which means we need to make this positive and that positive, which is where I got those expressions from.
Got it. Thank you. That makes so much sense.
Yeah, absolutely.
So, instructor,
Of course.
I'm not certain if you already mentioned this before, but because we're looking for positive numbers here for our array, and if we were having to get a negative number, how would we convert that to being stable?
So if that negative number in the left-hand column doesn't have any k's in it, that means that you cannot stabilize the system with the controller architecture that you're analyzing.
Gotcha.
Yeah. So if this 3 had been a -3, we'd be hosed.
Oh, okay.
I mean, then the question would be never. Like there is no combinations of kp and ki that make this closed loop system stable.
Exactly, with this given controller or game.
Right. So then, like in reality, it would be, okay, then a PI controller isn't sufficient. Then you would have to go back and try a different controller architecture.
Gotcha. Thank you.
I had a question as well, if it's okay.
Yeah. Go ahead.
So you said something kind of interesting earlier. This implied
No.
that that higher order systems tend to be harder to design.
Uh-huh.
So it would be preferable to have a lower order system.
Well, if your objective function is how easy your job is, then yes. If your objective function is to build a better system, that's going to be harder. Like in very broad strokes, that is a harder thing, but it is a more desirable thing for the people who are paying you to do your job. So yeah, it would be nice if all we ever needed was first order RC filters. Like that's great. There's only one parameter to find. You just find the time constant, and then you give it to the tech and say, okay, pick a R, pick a C, make sure they multiply to be this number, and then I'll be out getting lunch. But you're not going to get paid very much for that. So if you have more degrees of freedom, so if your low pass filter, say, is fifth order, then you get a lot more knobs and dials that you can adjust. It's going to be harder to design, but you're going to have a better performing system. And that results like holds true almost across the board. Is the more, I mean, it's a trope in this class, but the more control you have over a system, the better you can make the system.
All right, thank you.
Yeah, you're welcome. Okay, so that was a couple of examples in the case where everything is basically playing nice. We also have other cases that can pop up. In particular, some of you might have been concerned that in the Routh-Hurwitz, in the Routh array construction, we're dividing by numbers. And if you have like a CS background, then you might, okay, if my algorithm divides by some random number that you're going to provide me, what's to stop that number from being 0? Right? If you have a very algorithmic way of, or a machine arithmetic way of looking at things, that probably would have occurred to you. And so there is a special case for when there is going to be a divide by 0. All right. So the procedure is take the thing that was going to be 0 and pretend it's not. Pretend it is some other thing that's not 0, call it epsilon, and then carry on, basically, as if nothing's wrong. Then you can divide by epsilon because as far as you know, epsilon is not 0. It's basically pretending everything's fine. So we're all good at that. Sorry, more Monday creeping in. At the end, once you've built the array, then you are free, or you have to take the limit as epsilon goes to 0. Okay, so then once you do that, you're going to count as normal the sign changes in the left-hand column. So I have this, because what I just said kind of, it's a little abstract. So let's run through this example. Okay, so I have left myself virtually no room, but let's make the most of it. This is a fifth order polynomial. So 5, 4, 3, 2, 1, 0. Okay, and then we go 1, 2, 2, 4, 11, 10, and then zeros. Okay, so here straight away, when we work out b sub 4, this is 2 times 2 minus 4 times 1. So the b4 works out to be 0. So at least we get the payoff quickly here. And so the procedure says, stop, collaborate, and listen, and replace the b sub 4, which would have been 0, replace it with epsilon. And then continue on your merry way. Okay, so let's try it out. B sub 2 shouldn't actually be touched by epsilon. So what do we get? We get 22 minus 10 divide by 2. Call that 6. And then this b sub 0 is actually going to be 0 because of these make-believe zeros out here. All right. So here is where the epsilon pays off, because to calculate c sub 4, we would normally be dividing by b sub 4, which would be 0, but now it's epsilon. So let's do c sub 4. This is going to be 4 times epsilon minus 2 times 6 divided by epsilon. Okay. That's fine. You could reduce this a little bit further if you like, but let's leave it in this form for now. And I'm not going to write that in there. I'm just going to assume that C sub 4 is living over here. Let's do C sub 2. Ooh, C sub 2. That's an easy one, right? It is 2 epsilon 10 and 0, which means we get to teleport the 10 down here, which would have been real hard to do if we had been trying to divide by 0 here. So again, the epsilon comes to our rescue because we can multiply by 0 and divide by 0 as long as the thing that we're, sorry, we can multiply by epsilon and divide by epsilon provided it's not yet 0. And then nothing breaks with the world. Okay, so let's do the D sub 4. So D sub 4 is going to be 6 times C sub 4 minus 10 epsilon divided by C sub 4. And if you work this out, you get something like 6 minus 10 epsilon squared divided by 4 epsilon minus 12. And what do we get for this? We get, well, we can imagine a 0 there, which means we get a 0 there, which means we get to teleport the 10 again down to there. We've done step 1. We've done step 2. And now we have to do step 3. We have to take the limit as epsilon descends to 0. So if that happens, then this is positive. This is positive. And as epsilon descends to 0, it is always positive. So that's why we get to count this epsilon as a positive. Now here is the tricky bit. Take the limit of C4 as epsilon descends to 0. So epsilon is always positive, but it's going to get very, very small. So tell me, what is the sign of C4 as epsilon gets small?
Negative.
That's right. So this term is going to become tiny, which means that the numerator will become negative. And if the denominator is always positive, then C4 becomes big and negative. Big and negative. Over here in the array, I'm going to attach a little negative sign here. And what happens to D sub 4 as epsilon gets small? Well, this denominator gets negative, and the numerator is positive, but we've got the negative out here. So actually, D sub 4 becomes positive in the limit. So this is positive as epsilon gets small. Okay, so we are ready to count the sign changes. And I think, by my count, this is the first time we've actually had sign changes. So let's hop down the row here. This is no sign change. This is no sign change. This is one sign change. This is another sign change. And this is no sign changes. So we look at the number of changes. We just sum up these red numbers. So there are 2 right half plane roots. All right, so as I was afraid of, I said that we'd have plenty of time, and we don't have plenty of time. So rather than rush through the last case, which is a special case of the special case, let's do that on Wednesday. So heads up, we're going to finish Unit 4 on Wednesday, but then we'll start Unit 5 on Wednesday. So it'll be the first time that we bridge 2 topics in one lecture. That means we have a couple minutes for questions, so I'll open up the floor.
Professor?
Yes.
Would you please explain how you conclude as 2 R as roots from the sign change?
Well, how many sign changes are there?
2. That's the reason why.
Yeah, I mean that's what the Routh-Hurwitz criterion says.
Oh, okay.
Um,
Oh, yeah, got it.
yeah.
Okay, thank you.
Yeah, so the goal of this example wasn't explicitly stated, but if your goal is to determine the number of right half plane roots of a polynomial, which is probably what you're trying to do if you're doing Routh-Hurwitz in the first place, then this is the procedure you would use. And again, this procedure is only necessary in this situation. So we're in this situation because B4 was 0, but B2 is non-zero.
Okay, so does that mean the system is not stable?
So yeah, we didn't actually frame this in a system context, but if this were some transfer function, h of s is some numerator over this polynomial, which I called p of s, then all of a sudden we can say this is unstable.
All right, thank you.
Professor, I was going to ask you, it was kind of easy to find it with two unknowns, but say if we find the sign changes with two unknowns, but what if we had 3 or 4 unknown variables in our control system? What methods would be used for those?
You would be careful in applying the methods that we learned here. When you get above 3 or 4 unknowns, then, or when you get above a couple of unknowns, then all of a sudden it becomes real hard to visualize, right? Because you lose the ability to plot things in a plane. So maybe you can plot it in 3 space if you've got 3 degrees of freedom, but anything more than that, you're going to need to start talking about, if you want to visualize, then you need to say, if the 4th degree is this, like fix that, then you can plot the 3 space of the remaining 3. And then you can try and iterate that and show that kind of, but yeah, the ability to visualize becomes way harder as the number of dimensions increases. But the practice is actually, it's no different. It's kind of like in your linear algebra class that you would, like you could solve for the inverse of a 5x5 matrix. It becomes really hard to visualize what a 5x5 matrix does to any particular vector, but you could still describe what it does. So it's the same idea that you would have a bunch of inequalities. It'd be really hard to visualize what they mean, but you could come up with k's and then check them against those inequalities.
Okay. Yeah, because I wasn't sure if that was like, yeah, just a different method of solving all these variables, but that makes sense. Okay. I was going to ask you too, what would Kp plus Ki over S be? Would that be some sort of controller or?
Yeah, so if you look at it, the name is pretty much exactly what it does. This is, so what does this controller do? It says, give me the error, and I will scale it proportionally to Kp, and then give me the integral of the error, and I will scale it proportional to the integral of that error. So this is what I would call a PI controller. Sorry, not just me. This is called a PI controller because you act on both the error proportionally as well as the integral of the error. All right, we've got to leave it there, and I will catch you all on Wednesday. Thanks, everyone.